Okay, what we're going to look at today is Chapter 6, ultimately looking at all the classifications and nuances of stereochemistry as far as we're concerned for the rest of the semester. In theory, this lecture will cover everything from Chapter 6, and then on Wednesday's class, we'll go through and work some problems. So try and think of as many questions or work as many homework problems as you can to try and get a better understanding of where you're going to have problems with the material so that you can ask questions in class. So we'll go ahead and get started, almost started. One thing I do want to address is that I made a fairly major mistake and forgot to ask any questions in Exam 1 about pretty much chair conformations. So Exam 2 is going to have questions on chair conformations. So just remember that. They will show up. Sorry if you spend the time studying for that material. I just forgot to do it. So to start off with, we've got our cyclic structures, which was what we were just talking about there. And one of the things that we needed to learn from that was our cis and trans, same side, opposite side. So let's kind of look at a quick example here. So if we looked at a methyl cyclohexane, we could just draw on a CH3 and we would have methyl cyclohexane. But if we now make it 2-methyl or dimethyl cyclohexane, we could draw a variety of different structures that would then match this. Okay? So the easiest way to represent those different isomers is to go through and show our wedges and dashes, specifying that in this case the methyls are on the same side of that cyclohexane. We could also go through and do it where they were trans, and in that case we'd use a wedge for one and a dash for the other, and we've got our trans. Okay, so that's probably the easiest way to go through and see cis-trans isomerism or cis-trans relationships. The other way that we could go through and see this is if we went through and looked at chairs. Okay, so if we drew out a chair conformation, so we can draw one of our chairs, we can draw a methyl up and a methyl down. In this case, our chair implies that three-dimensional structure, and our CH3, now circled red, is aimed in the up direction, and our CH3 in green is aimed down. So if one's up and one's down, we have a trans conformation. Where this becomes a little bit trickier is when you're looking at the equatorial positions. So if we go ahead and draw another chair, and we'll stick with the trans for the moment. If I want to now show this equatorial, I could go in and throw in my CH3. Oops. Let me erase that for the moment. Maintain our same colors. Let's go through and draw in that same CH3 in our equatorial. So there's our CH3. You'll notice that that is aimed more or less down. Okay, which isn't always the easiest thing to see, so what you could do is go through and draw in the axial position. If you're going to draw it, make sure that you specify that you're not looking at a methyl out there. So you have to specify that hydrogen. Otherwise, if I'm going to go through and grade, I think that's a methyl. Okay, so that would be our CH3 in the down direction. If we wanted to show our other CH3, equatorial again, and we want it to be in our trans conformation, we could go through and put our CH3 here. Okay, and that is now up. Okay, and that is not the easiest thing to see, again, until maybe you show the axial hydrogen, and you'll notice that our CH3 is indeed aimed up. Okay, so be careful with your equatorial positions. Like I said, they aren't the easiest to go through and see and determine if it's up or down. Okay, but remember, your chair does imply that up-down information without the use of wedges and dashes. There is one more way that we can go through and imply this chemistry, and that's a Haworth drawing. Just going to draw a simple one real quickly here. So we could draw, okay, typically these are used for sugars, so I'm going to pretend that I'm drawing a sugar well. And in the Haworth drawing, what we're doing is taking, I was drawn terribly, let me try that again. In a Haworth drawing, we're taking a ring or a sugar structure, and what we're trying to do is imply some three-dimensional characteristics to it. Again, it's not going to work in that direction. We're going to have to draw it this way. Okay, and Haworth went through and said, well, you know, the cyclohexane is roughly a flat structure, so I'm going to pretend that instead of looking at this in the overhead, so if we drew out an overhead projection of this, we might specify a wedge and a dash for our CH3. Haworth went through and said, you know what, I'm going to say this is now my CH3 that's aimed up, okay, which I can go through and highlight in red here. There's my up CH3, and my down CH3 is attached to the next carbon, and we'll just draw that down. Okay, so Haworth just tried to imply that up-down characteristics by saying instead of looking directly from the top, okay, what we've done is kind of flipped these front carbons. I know this isn't the easiest thing to see, and kind of rotated it up ever so slightly, so that what we're seeing is those front carbons are actually all kind of wedged coming at you, and these back ones are kind of dashed going away from you. Okay, so the idea is that you're looking at it from the side. If I went through and drew in the hydrogens so that you could see those, there's our up hydrogen, and we can see our down hydrogen there. Okay, it's just another way to look at cyclohexanes. It's primarily used in biochemistry. We'll see it when we do lab assignments, because there's a model lab where we'll look at this kind of projection in the lab. It's not something I'm going to directly test you on. I just want you to be aware that there is another view for implying the cis-trans isomerism. So real quickly, just because we went through and did that, the conformation that we've got drawn here would be our trans. If we're going to draw the cis in a Haworth projection, we could draw the CH3, and we could draw another CH3. Okay, you'll notice that does get a little bit crowded. One of the reasons why I don't particularly like it, but hey, it works, and it's very, very commonly used when you're dealing with biochemistry, in particular carbohydrates. Okay, so just kind of be aware of that. Ultimately, you will need to understand this cis-trans relationship. Okay, we're going to see it pop up again when we look at the alkene functional group, and it's going to come into play in this next chapter when we're trying to decide cis-trans and then identify the relationships between structures. Okay, so just remember that. Hopefully it's fairly straightforward and you already remember it all anyway, but just in case. Okay. The next thing we've got to look at is classifying our pairs of molecules. And you were already tested on this, and you're going to get tested on it again. It's something that's going to show up consistently throughout the rest of the semester. Okay. So you need to be able to follow the flow chart and try and determine what things are happening as you move through it. So given any pair of molecules, we address first, do they have the same molecular formula? If no, then we know they're different. If yes, then we still have some relationships to go through. We can look at superimposable. Okay, our atom connectivity, which if you get really good at nomenclature, instead of looking at the same atom connectivity, you could look at same, and I'm going to put it in quotes as far as our same, because we're going to change that in a little bit today. Same name. If they have the same name, if that's a yes, then they're stereoisomers. If it's a no, then they're structural isomers. Okay, so it's effectively the same thing as same atom connectivity. Okay, and then the last big question to ask is mirror images. When you go through and apply these definitions, the two most difficult ones to interpret end up being the superimposable and the mirror images. Okay, pretty much everything else I think is roughly fairly straightforward. You should be able to do those fairly well at this point. The issue with superimposable and mirror images is that more than often it's going to require drawing multiple different angles or structures or building models, or if you're just one of those great awesome people that can see it in 3 dimensions. If you're not, don't feel bad, because I'm not either. I particularly don't like this chapter because it requires lots and lots and lots of drawing. So our two kind of new definitions, if you will, would be looking at our enantiomers and our diastereomers. We do have an extra refinement as well with meso compounds, which comes from having an identical relationship between two structures. That structure would also then have to have at least 2 chiral centers. Okay, so if that's a yes, then it's meso. If it's a no, then they're just identical. Okay. Meso and identical are ultimately the same thing. Just so that you're aware, it just comes down to which is the better definition. How do you actually want to apply it? So meso makes a little bit more sense. Okay. Next big thing is looking for chiral carbons. So one of the big red flags for identifying all of these things is finding a chiral carbon. So it's helpful to know what a chiral carbon is. Otherwise, you just have to apply those definitions. So chirality or chiral centers, stereocenters, chiral carbons are all ultimately kind of getting at the same thing. And what we're saying is that the structure or the compound, whatever we're looking at, its mirror image is not superimposable. Okay, so we've taken the two hardest definitions, essentially, are mirror images and superimposability. Okay, so what we need to do is look at the mirror image and then spin it, rotate, flip, do whatever you need to do to see if you can take that mirror image and superimpose it on the original. Okay, so if we take a look at the example in our lower right hand corner, if we just try and copy that right structure over, you'll notice that we just try and pick it up and shift it on top, that if we drew this on, we've got carbon 4 going back here, carbon 3 over here, and carbon 2 there. So that clearly doesn't superimpose. Okay, carbon 1 overlaps, so that's nice. So what we could go through and do is say, okay, carbon 1's in the correct spot. So what I'm going to do is hold on to that, and I'm just going to rotate around that bond. So what I'm going to try and do is swing carbon atom 2, or atom number 2, over to the other side of the structure. So in the process of that rotation, I know it's going to be kind of small, but we'll draw it down below. If we take our center carbon atom, atom number 1, our green atom, never changes places because we're rotating about that bond. So that stays in the same spot. Carbon atom number 2, however, is going to fully rotate around, and we're going to rotate it so that it stays in the plane of our drawing. Okay, so we'll draw it with a solid line. Okay, and I have to add these with the next few things with wedges and dashes to imply that stereochemistry. Okay, as we go through and rotate it, atom 3 was wedged coming at us. I'm going to pick orange for our yellow. And atom 4 was dashed going away. As we do this rotation, atom 4 is then going to continue to rotate around, and you'll notice it's going to swing around the backside first. It's going to come out being wedged. Okay, that's what that was an attempt to show. If we take a look at atom number 3, as we do that rotation, it's going to come out dashed. If we now try to overlay these, so what we're going to do is we want to see how this new rotation overlays on top of our original. And you'll notice that carbon atoms 1 and 2 overlay perfectly. So that's great. We do have some superimposability. Okay, so we would have atom 1 line up and we have atom 2 line up. Great. But what happens on the other side with 4 and 3? Okay, well, 4 was wedged coming at you, and 3 was dashed going away. Okay, well, if we look at the structure that's actually there, carbon atom 3 is supposed to be wedged, which means these two aren't superimposable. Okay. For those of you that think this is really, really easy, that's probably because you can see this in 3 dimensions. Okay. For those of you that think this is hard, it's going to involve drawing a lot more structures, like what I'm trying to go through and show you here. Okay. It can be a bit frustrating at times. Go through it as slowly as you can. Try and do those rotations. Try and do those superpositions to see if you can figure out what's going on with it. Okay. So if you do have a chiral molecule or chiral structures, atoms, bonds, hands, you'll notice that if you look at the mirror image, it's not superimposable on the original. Okay. What we're concerned about as far as organic chemistry goes is identifying a chiral carbon. Okay, so we just have to find a carbon that's non-superimposable on its mirror image, and now we're looking at one of those fancier stereoisomers. Okay. If you find one, ultimately you're classified as either an enantiomer, diastereomer, or potentially even meso. Okay, if you don't find one, you're in one of the other classifications. Okay, so kind of be aware of that. It can be easier to go through and identify or find those compounds or those relationships by looking for these chiral carbons. The example given here is primarily given because it simplifies things a little bit, and that one of the big red flags to look for is identifying or finding 4 different things attached to a single carbon. If you get those 4 different or distinguishable things, that carbon atom, the center of those 4 things, ends up being the chiral carbon. Okay. In some cases, it's straightforward, like very clearly here, they're numbered differently and they're colored differently. But that difference doesn't always happen immediately. Okay, you might see that difference further on down the line. We'll take a few examples of that a little bit later. Okay. If you have an achiral compound, when you draw the mirror image and then try and superimpose, you find out that you can indeed superimpose everything. Okay. This means you're not looking at a stereoisomer. As long as we classify mesos as not stereoisomers, we'd be okay with that. So you'd get meso, identical, or the other ones, different structural isomers. Okay. If you take a random object and you try and run this process, you can also find out that that compound is achiral, or that structure is achiral. For instance, if you took a pencil and you try and draw the mirror image of a pencil, you'll notice that it is superimposable on the original. Okay, it doesn't have any chirality associated with it. The other thing you could go through and do as far as organic chemistry goes is look for a carbon atom that only has 3 or less things attached to it, different things attached to it. You'll notice one of the patterns that we're going to find out here is that because we need 4 different things attached, the carbon atom itself, okay, in all of these examples, has a very particular patterning around it. You'll notice it always has 4 bonds, okay, or is sp3 hybridized. What happens if we say shift to an sp2 hybrid? Okay, if we had an sp2 carbon, let's say this guy, let's go ahead and even make this really different, chlorine, and let's put a fluorine here. If we tried to evaluate if that center carbon is chiral, we'd go through and look to see how many different things are attached. And when you go through and label that, sure, chlorine's different than fluorine, so there's 1, 2, and both of those are different from oxygen, which is 3. There's 3 things attached, okay, or 3 unique groups, which means our chirality, those comparisons are really only going to come through when you have sp3 carbons. If you have an sp2 carbon or an sp carbon, you can immediately eliminate that from your discussion or thought process as far as this class is concerned. Okay, there are definitely exceptions to that. I'll throw one of those exceptions on the quiz or the problem set that we'll work on in class. Okay. Irritating. Okay, so let's continue on to the next slide. This just kind of summarizes all of that material. You'll notice that when your textbook goes through and ranks this, they talk about the enantiomers first, then the diastereomers, then the meso, and kind of give you different examples as you move through it. Okay. Ultimately, we're concerned about condensing those all into one big giant thing. Okay. So definitions that can come in handy. If you wanted to apply them, it's kind of up to you. Your meso compounds, you'll notice, will always be achiral. By definition, they are superimposable mirror images, which means they have to be achiral. Okay. The one thing that's going to help you, or a couple things that might help you with meso compounds, is you will notice that they are an identical comparison between those your two structures, and they will have at least 2 stereocenters. Okay, so that's a requirement for it to be meso. One of the other things that you might find within it is an internal mirror plane. Again, it must have at least 2 stereocenters. Okay, because if you take 2 identical compounds, for instance, if we take butane and compare it to, say, this structure, both of those are butane, we would say the relationship between those 2 compounds is identical. They don't have stereocenters. Okay, or neither of them have stereocenters. Even though they do have an internal mirror plane, they are not meso. Okay, that compound is not meso because it doesn't have those 2 stereocenters. Okay. After that, we could take a look at our enantiomers. So that's where we get our 2 primary definitions, or 2 primary rules for our enantiomers. They have to be non-superimposable, and they have to be mirror images of each other. Okay. You'll notice that enantiomers will be chiral. They fit the perfect definition for chiral molecules. Okay. The next thing that we could, or the next definition, is we can look at diastereomers. Each compound, so diastereomers are a little bit trickier. It's a little bit harder to call them chiral because diastereomers is really going to only apply to a pair of molecules. So I'm going to kind of cross that out because that's kind of an odd comparison to go through and say. They will have at least 2 stereocenters, so they're similar to the meso compounds in that respect, except they will not be superimposable. Okay, the best definition I can give you for diastereomers is that they're not enantiomers. I know it's a crappy definition, but it works. Okay, so if we go through, we can just apply the rules of enantiomers and just kind of go through and switch it. We're looking at non-superimposable, and the primary big difference between enantiomers and diastereomers is that we're looking at not mirror image relationships. Okay. So now that we got kind of an idea on what we can do with this, chiral, achiral, all that kind of fun stuff, we're going to start to apply it and look at a couple examples and kind of push from there. Okay, so isomers. What we just went through and did is found the relationship between 2 structures, and if they were the same, they were our same formulas, they were ultimately isomers of each other. Okay, so what we're going to go through and do is look at something a little bit different. We're going to look at the isomers possible for a single name. Okay, so one of the things that we just went through and did with all of that was identify all those special different relationships between those compounds. Well, maybe those compounds will impact our names. So if we go through and look at this compound 1,2-dichlorocyclopentane, structures given for you, okay, we want to go through and see what possible isomers there are. Okay, and this is where our cis trans is going to come into play. Okay, so when we take a look at our structure, you'll notice that I haven't implied wedges and dashes on those chlorines. Okay, so then the question is, should I? Well, if I made this chlorine dashed versus making it wedged, okay, does it see a different environment? Okay, it sees the top versus the bottom of our ring. Okay, so let's freeze our ring for the moment. Say, okay, yes, it does see a slightly different environment, which means I need to specify wedges and dashes on my individual compounds. Okay, so when I go through to try and solve a problem like this, where we need to find all of the possible stereoisomers, what I'm going to do is pick one of my stereocenters, and I want to draw the possible combinations for it. So let's pick the left one. I'm going to make that one wedged. Okay. We'll go ahead, why not, show the lone pairs. Okay, and I know there's two possibilities. Okay, so it can be either wedged or it could be dashed. Okay, so we could draw that in. And we've got those two options. Because I have another stereocenter, okay, I have to realize that that stereocenter is also going to have an impact here. So I could go through and pick it. And I know that chlorine can either be wedged or dashed again. So I'm going to go through and say, in my first case, let's go ahead and make it wedged. Okay, and because it could be dashed, I'm going to go through and only change that one conformation. So the other one, my first one, I'm going to leave, okay, as the wedge, and then I'll go through and show that other chlorine as dashed. Okay, but remember, I also have the possibility of my initial chlorine being dashed. So now I need to go through and do that same comparison that I just went through and did, but now with my first chlorine being dashed. Okay, so I can say that second chlorine is wedged, or that second chlorine could be dashed. Okay, and so what we've got are four possibilities. Okay, so one of the patterns of someone much smarter than I and mathematically inclined could probably notice is that for each chiral, let's not mention chiral centers yet, for each of these positions we could either have a wedge or a dash. So there's two options. So mathematically we could go through and say, oh, okay, well, if there's two options, then it's got to be 2, and depending on how many different positions that I can have wedged and dashed, we'll say 2 to the n power. Okay, so that's what's happening here. If you aren't, whoops, that was supposed to be an eraser. If you aren't super comfortable with that, that's fine. Just remember 2 to the n, where n equals the number of these wedge dash possibilities, okay, that would be different. You'll notice that when we go through and count this, that I've only shown, not quite yet. Let's go through and put on hydrogens. We could go through and say that this hydrogen was wedged and this hydrogen was dashed. Okay, that's perfectly valid, but now I've got more wedges and dashes. Should I count that as one of my n? Okay, and the reason we don't count it is, what's the other position? It's a hydrogen. Well, hydrogen versus hydrogen, do we really see much of a difference there? No. In the other cases, we're looking at hydrogen versus chlorine, we do see a difference there, so it makes sense to specify our wedges and dashes. At our bottom case with those other hydrogens, it doesn't make sense to specify those, so we won't count those as my N possibility. Okay, so what we're looking at here is two possible orientations for our wedges and dashes in two different positions. So our calculation, as far as finding our maximum number of stereoisomers, would be 2. Let's try that again without the eraser. 2 to the second power, which equals 4. Which means if I'm going to draw everything out, I should end up with 4 possible structures. And as I'm sure you could count, we've got 4 possible structures. So we've drawn all possible stereoisomers for this name. Okay. Taking a step further, let's go through and figure out, or try and come up with a better way to specify that N. Okay, so as the rule is stating down below, is what we're looking for is our stereocenters, or our chiral carbons. Okay, so let's go through and pick any one of these. So I'm going to pick the upper left, and we're going to try and identify if those two positions are indeed stereocenters. Okay, where we said the wedges and dashes needed to be shown. Okay, so if we go through and label this out for, I'm going to label them blue and green here. Okay, so if we take a look at the blue one, I've got a chlorine. Sure, that's different, so we call that 1. There's technically a hydrogen down there, so that for sure is different as well. So chlorine versus hydrogen, those are two different things. Versus a carbon, also different. If we look at the next position though, the next atom bound is also a carbon. So is there a difference between that carbon and our 3 carbon? Okay. In theory, you might be able to immediately say, yes, there is a difference. In one case, one's bound to chlorine, one's bound to hydrogens and carbons. Okay, and that is ultimately what we're going to do. As long as we can tell the difference between those two carbon atoms, we're fine. So what you can envision is if you built the model of this, tossed it up into the air, okay, let it spin, flip, do whatever it wanted, would you be able to distinguish or always point to this carbon as opposed to carbon number 3? If you could always do that comparison and always be correct, then you know what? What we're looking at is a stereocenter, or those two are two different positions, which means we have 4 things attached to a single carbon. This carbon is now a stereocenter. So there's one of our N. We can go through and do that with our green carbon as well. Again, we've got our chlorine, we've got that hydrogen hiding back there, so there's 2. There's our 3 for our 3rd carbon, and we end up looking at our other position, our other carbon there, as 4. Okay. If we tried to go through and do that with any one of those other carbons, so let's pick one that's kind of far away, and let's show on the other 2 atoms that are out there, we've got our hydrogen and hydrogen. If we tried to go through and number these, hydrogen for sure is different, so there's 1, but what's the difference between that hydrogen and, say, this hydrogen, the one right next to it? We can't really tell a difference between those. They're both hydrogen, which means they both get labeled 1. I can't have 4 different things attached. Okay, so no chiral center as far as that red atom goes. Okay. Why is it flashing? Okay. So, what we now have, 2 stereocenters, great. Okay. So now that we've got all that kind of settled, and we've got a little bit of practice under our belts, now what we're going to try and do is identify the relationships between these. Okay, all of the relationships between our structures. Okay, and this can be a bit tricky, and I drew them a bit close to each other, so it's going to get kind of messy, just so that you're aware. And I'm actually going to erase this to clean that up a little bit. Okay, so I'm actually going to pause, magic of video recording, and we're back with beautiful pictures. Okay, so we want to try and find the relationships between these. So I'm going to take a look at the relationship between, let's say our first two structures. Okay, so what we would go through and do is apply all of our definitions that we've looked at before. Same molecular formula, yes. Superimposable, no. So if we tried to overlay this on top, we might notice that our chlorine wedged would match up with that chlorine wedge, so that's nice, but then our other chlorine that's dashed wouldn't overlay. Okay, so they're non-superimposable, which means we aren't looking at identical, so that helps simplify things a little bit. We would then move to same atom connectivity or same name. Well, we drew these coming from the same name, so we know they have the same name, which moves us to the next issue, mirror images. Okay, if they were mirror images, we don't change the wedges and the dashes, they would stay the same. Okay, so since one's wedged and one's dashed in our rightmost structure, clearly something has changed from the wedge-wedge, and we're looking at not mirror images. So these are non-superimposable, not mirror images, which means we are looking at, good answer, diastereomers. Okay, if you weren't able to follow all of that, I don't blame you, that was pretty fast, and I'm just going to leave it at that. You could go through and make sure you've got the flow chart in front of you when we go through with the rest of these. Okay, how about between these two structures? Okay, and I'll do this one even faster. We're going to end up calling those diastereomers as well. Okay, we're going to end up again in the same position, non-superimposable and not mirror images. Okay, how about the relationship between, let's go ahead and pick these two on our far right. Okay, and you should be able to see in theory again that the relationship is that these are again diastereomers. Okay, how about on our far left, the relationship between these two? Again, we'll notice diastereomers. Okay, so that's interesting. We've got a relationship between all of those individually diastereomers around our ultimate loop. Okay, well, what's the relationship between, let's go ahead and do blue across the diagonal. Okay, so if we try to go through and do this superimposable, so we've got to be further up in on our flow chart, so we got the same molecular formula, but now are they superimposable? If we try and directly overlay, you'll notice that we're dashed versus wedged. That doesn't work. Okay, so instead what we can do is pick one of those structures, either one, and let's go ahead and flip this one over. If we flip it, what happens? Those dashes will become wedges, which then means I now have superimposable structures. So I could go through and call these identical. Okay, but is there a better relationship here? Okay, can I call that something a little bit more appropriate? Do I still have two chiral centers? Well, if we go back maybe 5-10 minutes, I went through and said that those two positions were stereocenters, which means the best way to identify the relationship between these two compounds is that they are meso. Okay, if it is indeed meso, then one of those compounds doesn't count as a stereoisomer because it's ultimately the same thing as the other. So we can cross this one off, and really we only have 3 stereoisomers. But our formula said that we should have had 4, right? Okay, if we go all the way back to that. That's the maximum number. Okay, not the exact number, but the absolute maximum you could have. If you have a meso compound within that possible realm of isomers, you lose one structure from your total. So for this individual compound, we can only draw 3 possible stereoisomers, okay, because we have this meso complication. Okay, well, we aren't quite done yet. We also have across the other diagonal. Okay, the relationship between those. If we try to superimpose them directly right now, you'd notice that that does not work. Okay, so we could try to flip one. So let's go ahead and try and flip this bottom one. Okay, this is not going to be the neatest thing, but I'm going to attempt to draw the flip here in the lower just below that. So if we go ahead and flip kind of that direction, okay, the chlorine that is dashed is now going to be wedged over there. Okay, and the chlorine that is wedged is now going to be dashed. Okay, you'll notice that still doesn't quite overlay perfectly, so what we can do is rotate a little bit and we can get our chlorines into the correct positions, and again we end up with non-superimposable. Okay, so the relationship between these two structures is they are indeed non-superimposable. The last thing that we could go through and try and do is draw the mirror image and verify that they are mirror images. I'm going to leave that one for you to do because I've definitely made so much of a mess of this page that we can't really follow anything anymore. So I'm going to leave you to draw and find out that indeed they are mirror images. So if we're looking at non-superimposable mirror images, the relationship across that diagonal is enantiomers. Okay, kind of makes sense, hopefully. So what we've got to go through and do is draw all our possible combinations. Okay, if I ask the question, just tell me the maximum number of stereoisomers, you could just use that formula to tell me what that maximum number was. If I tell you to tell me the possible isomers, that gets a little bit trickier. You'd have to evaluate your structure and decide, is it possible for an internal mirror plane? So if we looked at the initial drawing, okay, the one that actually looks nice, we could go through and say that, yeah, I do have a mirror plane, an internal mirror plane, which means I have a meso compound. I have one less than the maximum number. Okay, if we had two mirror planes, we could then go through and say we've got two less. Okay, so you can subtract one for every mirror plane that you identify. Okay. Hopefully that makes sense and you can kind of deal with it. I know it is a bit troublesome to go through and draw all these out and figure out the relationships between them. It just takes practice, okay, and that's what we're going to do in lecture on Wednesday. Okay, so then we can push to the next real big question. Why do we even care? Why are these differences important? And that's where we can move to this drug thalidomide. Okay, thalidomide was a drug back in the late 1950s, I believe, and it was designed to cure morning sickness, okay, for pregnant women, which is pretty nice. So they could take this drug and then they didn't have to be worried about being sick, presumably. I'm going to guess that's a pretty rough thing to have happen. I actually wouldn't know anything about that, go figure. But this drug had some interesting, unfortunate is a better term there, some unfortunate side effects. So that ultimately all really came down to the structure itself. So they noticed these side effects and wanted to figure out what was going on with it. So what I'd like you to do is take a look at this compound. So you can go ahead and pause the video now and try and identify if we have any chiral centers within that molecule. Okay, so see if you can find them for me. You need a hint. What we need to do to find our chiral centers is to identify a carbon that has 4 different things attached. So we could go through and individually identify all of our carbons. You may realize that the ones I've now highlighted in blue cannot be chiral centers. Okay, why not? They're all sp2 hybridized, so those can't possibly be chiral centers. So then the next option is going through and identifying our only other carbons. There's only 3 of them. Okay, those 2 red carbons, each are sp3, which would work, but we only see 2 bonds, which means there's 2 hydrogens also hanging off of those. Our last option is right here in the middle, It's also sp3 hybridized. 3 bonds shown, 1 bond then left over is our hydrogen. What do we have here? There's our chiral center. So really, thalidomide has 2 versions. One where that bond is wedged, and one where that bond is dashed. Okay, super subtle difference. Okay, so one of those conformations ended up curing morning sickness. Great, fantastic. The other one ended up, for those of you with unsuitable constitutions, maybe, might be a pseudo-nice way to say that. Be aware, we're looking at a disturbing picture. Generated birth defects. Okay, so you can look this up on Wikipedia if you'd like. There are all sorts of pictures and images from this drug. Okay, it ended up causing massive mutations within the external limbs, and it was ultimately all due to that chiral center. Okay, and how the compound was processed within the body. Okay, so it turns out that these differences are extremely important, which means we need to be aware and cognizant that they exist, particularly in any field that's dealing with drugs. Okay, which brings us to our next issue. With the last example that we just went through with the 1,2-dichlorocyclopentane, you notice all of those were named the same thing. Well, one of those could have been just like thalidomide. Maybe one version of it cures a particular disease. The other one causes or kills or does something really damaging. So we need to come up with a new nomenclature system to identify it. So we have to somehow monitor and keep track of this information. So there's 2 things that we can evaluate here. One is the absolute configuration. So when we go through and draw structures, which is ultimately what we've been doing for the whole semester, we need to be able to come up with a nomenclature system that allows us to differentiate between 2 different compounds. Okay, one with wedge, one with dash. Okay, so those rules are our Kahn-Ingold rules. We define those as our absolute configuration, and those are based on ultimately theory, what we have drawn for us. Okay, theory is great, and having a structure would be great, except that we can't see structure. So being able to come up with a absolute configuration is nice, but it doesn't work in the real world where we don't have those structural things. So we needed to come up with some kind of experimental relationship or experimental discovery to determine which isomer that we ended up obtaining. Okay, and that's where we get our relative configuration. That is determined through experiment, and that experiment has ultimately optical activity. These 2 configurations you would hope were related to each other. I've heard rumors that they tried to build a system where they were related to each other and then just couldn't quite put it together. Okay, so when we discuss these are 2 separate, independent configuration rules. You need to make sure that you treat them differently, even though they are extremely similar as far as how they're put together. Okay, and we'll address that a little bit more as we go through it. Okay. So our Kahn-Ingold prelog rules, or identifying or assigning R and S. So R and S is ultimately how we've gone through, or how we're going to end up going through and comparing these things. You notice that we can't use cis and trans if we had a more complex structure. For instance, if I added another chlorine out here, okay, we could go through and say wedge dash, and now the relationship between those 2, sure, that's going to be trans. But if I add another wedge out there, okay, I could then say, well, these 2 are trans, but then if we look across that ring, these 2 are cis. So how would we name that structure with so many different stereocenters? So we wouldn't be able to use the cis-trans nomenclature system, and that's where R and S are invented, or why they were used. Okay, so the first thing that we would have to go through and do in all cases is identify a chiral carbon. Okay, and we've already started to go through and do that. That's just trying to find a carbon that has 4 different things attached to it. So in the case that we've looked at already, we would go through and label those as our chiral carbons. The next thing is to assign a priority number to each of those individual 4 groups attached, which is where we get this 1, 2, 3, 4 ranking system. Okay, so priority is assigned always according to the atomic number of the atom attached. Okay, so if we go in and take a look, I'm going to simplify our example here and just pick one of those as our chiral center. We'll go ahead and call that one our chiral center. We want to assign our priority according to our atomic numbers. Remember, we're trying to find 4 different groups, so let's make sure that we see all 4 different groups. So let's draw on that last hydrogen. Okay. For those of you thinking ahead, you'll notice I haven't drawn wedges and dashes yet. Okay, we're going to evaluate that in a little bit. Okay, so let's go through and try and assign priority to these. Okay, so our first rule is to give it the highest priority for the highest atomic number. So when we go through and rank, we'll compare our atoms immediately attached to our chiral center. And you'll notice, in theory, right away, that we can label 2 right off the bat. Okay, chlorine is absolutely our largest atomic number. I don't have a periodic table in front of me, so I can't tell you what number that is. Hydrogen is going to have our lowest, so we can nail down our 1 and 4 positions right away. Okay. The next issue is between our 2 carbons. Okay, we know they're different from each other, but we don't have a way to assign the priority because our priority is assigned according to atomic number. Okay, so what Kahn and Ingold came up with is they said, okay, if you don't identify a difference right away, look at the next atom along in the chain. Okay, and you'll continue to look at the next atom until you find a difference. If you don't find a difference, then there's no chiral carbon. Okay, so what you did was mislabel. So this might be an easier way to identify a chiral center than we had done earlier. Okay, the last rule on there we'll come back to quite a bit later. So let's go back and evaluate between these. We've got carbon and carbon. Okay, so no real difference there, so we can go through and look at the things attached to that carbon. We got hydrogen, whoops, I can't count, there's only 1 hydrogen, and we won't count our previous carbon, we won't do that one. So we got hydrogen, carbon, and chlorine. If we go through and look at our other carbon, we've got hydrogen, hydrogen, and carbon. So if we go through and compare our differences, hydrogen and hydrogen, same atomic number, which means no difference. So we'd eliminate that. The next thing is carbon. Okay, well, carbon versus carbon, also no difference. Now we go to chlorine versus hydrogen. Is there a difference in atomic number? Which one has the higher atomic number? Chlorine. That carbon then, okay, must be assigned a larger atomic or a larger priority number than our other carbon. So in this case, that one becomes 2, and our other one becomes 3. Okay? We can go through and do this again. In fact, I'd recommend you go through and do it again for our other position. So let's go through and erase that real quickly. Clear that all off. And let's take a look at our other carbon, or other stereocenter. We can draw on that hydrogen. And again, if we try and evaluate our differences, our chlorine is for sure going to be 1, 2, oops, that would be wrong. Let's try that again. We got hydrogen is 4, sorry about that. And now we have to identify the difference between our 2 carbons at the sides. Okay, when we go through and evaluate carbon versus carbon, no difference. So we can go out to a hydrogen, out to a hydrogen, no difference. So we can go back to our original carbon. Okay, and then we go back out again, chlorine versus hydrogen. Which one has the higher atomic number? Chlorine. That means this carbon, or the carbon that has the chlorine attached, must be assigned the higher priority number, and we'd go through and have that numbering. Okay. Takes a little bit of practice getting used to. That difference may be something that's extended fairly far around the ring, so you might have to shift all the way through. Okay. One of the interesting repercussions of this, as far as assigning our R and S, we have to assign it for every chiral carbon. Okay, each and every one, which means for the structure that we were just looking at, we would have to identify R and S configuration or our chiral configuration for both of these carbons. Okay, so you'd have to go through and do this numbering process for each one and make sure that each one is labeled in the name. I know you all love nomenclature. Here's where it gets messy. Okay, the very last step, so sorry that was a bit of a leap, at that point we haven't actually identified what our configuration is. We've just gone through and assigned these priorities. So the very last thing that we need to do is to go through and actually assign the priorities or assign our configurations. So what we're going to end up doing is taking our molecule, however it may be oriented, okay, and we need to change its position such that atom, our lowest priority, okay, in this case 4, is aimed away from us. It must be dashed when we go through and do our nomenclature system. Okay? If it is not dashed, you will name it incorrectly. So you must fix this. So in this case, what our drawing is showing is that we're going to rotate atom 4 backwards. Okay, so that means we're rotating about our carbon and 1 atom bond. And as we do that rotation, 3 will then come up on your left-hand side, and 2 will be on the right-hand side. Okay. Once that rotation's been completed, now we can assign R and S. What we will go through and do is draw an arrow starting from priority number 1 and shifting to priority 2, shifting to priority 3, and determine which direction we're turning, be it clockwise or counterclockwise. Okay. In this case, we're moving clockwise, which means we're looking at the R enantiomer. Okay. If we take a look at the example given below that, okay, you'll notice the relationship between these two, hopefully. What's that relationship? Good job. They are enantiomers. Okay. So what we're going to try and do is see what the relationship between our enantiomers are. So when we go through, again, atom number 4 is in the wrong position. That needs to be rotated so it's dashed going away from us. So we'll rotate the structure around. You'll notice that as we do that, 3 is going to come up on our right-hand side, atom 2 will be on our left-hand side, and we now have to go through and rank. Okay, so we'll go through, do the same process, moving from position 1 to position 2 to position 3. We're now moving in a counterclockwise fashion. What we're looking at is the S enantiomer. And sorry, my image overlapped our drawing. Okay, so what we have here is now our S enantiomer because we moved counterclockwise. Okay, I know that's a lot of information, so let's go through and try and process that with our compound below. Okay, you'll notice that this structure actually cannot be assigned R and S. Okay, and the question now becomes, well, why? Well, to do it, we have to know the relationship between all of our groups. Okay, what is the relationship between those chlorines and, say, those hydrogens? Are they cis? Are they trans? Same side, opposite side? We don't know. Okay, so to fix that, what I'm going to go through and do is pick one of the isomers. In this case, I'm going to make this wedged. And in the other case, I'm going to make that one dashed, so we can go through and process it in each case. It can be helpful to make sure that we see all of our groups, so I'm going to go through and put our hydrogens in there as well. Okay, so let's go through and rate what happens with our chiral center red, or our red chiral center. Our chlorine group is still 1. Our hydrogen is going to be 4. As we went through before, we said that carbon is 2, that carbon is 3. You'll notice that our hydrogen, our lowest priority, is aimed away from us already, which means we don't have to do any fancy manipulations. We can just go through and assign. We're moving from 1 to 2, 2 to 3. Which direction have I moved? I'm always backward of this, clockwise. So we have the R isomer, okay, or the R stereocenter at that position. If we went ahead and called that position number 1 with our name, we would then have to specify that at position number 1, that chlorine is relative to the rest of the structure in the R configuration. So we would say 1R. Okay, we have a second carbon that's a stereocenter, so we'll go through and specify that, and we'll leave that RS option open for the moment, and then we could go through and say 1, 2, dichloro cyclopentane. Okay, so the bulk of our name doesn't change. What we end up having to add is this extra RS configuration at the beginning. Because carbon number 2 is also a stereocenter, we're going to have to specify its relationship for everything else as well. Okay, so if we go through, let me erase all of that so it cleans up a little. Oh well, it's erased now. We can go through a number again. We've got 1, 4, 2, and 3. One of the most common mistakes at this point is to say, okay, I'm here, 1, 2, 3, which would say I'm moving counterclockwise, and I'd write S. If you write S, you're wrong. Okay, why are you wrong? Well, the last rule as far as assigning our chirality goes is we must have our lowest priority aimed away from us. That hydrogen is currently aimed at us. That's not going to work. Okay, so we have to flip or rotate the structure so that we can see it from the proper viewpoint. Okay, at this point it does not matter what the rest of this structure is. Okay, so what I tend to do is redraw it where it's simplified, where I get 2, 3, there's my 4, there's my dash going back to the 1. So I could go through and redraw to get that into the correct configuration. For me, I would rotate about my carbon 2 bond. Okay, as I do that rotation, 4 goes back, 1 ends up being here, 3 ends up being up top. Now when I connect through, which way are my arrows going? Here, let me do that in a different color. As I connect 1 to 2 and 2 to 3, which way am I turning? That ends up being clockwise, which means the configuration about my green carbon is R. I can now add that into my name. Okay. One thing to note, when we initially tried to do that one without doing the redrawing of it, we assigned the wrong configuration. Okay, it's either S or R, and we said it was S. Okay, if the hydrogen is aimed away, you don't have to do any rotations, you assign directly as is. If the hydrogen's aimed at you, change. Okay, so do your standard comparison. So we could go, whoa, drop the pen. We can go through and connect 1, 2, 3, okay, in that direction, which would say we'd have the S configuration, but we're looking at it from the wrong angle, which means we'd switch it to the R configuration, because the hydrogen is aimed at us versus away. Okay, when we get into class, one of the examples I'll end up doing is moving my arm in a clockwise fashion, okay, and then try and maintain that clockwise rotation and then turn around so that I end up facing away from you. And what you'll notice is that it appears, even though my hand is still moving in the exact same way that I was moving initially, that it looks like I'm now turning counterclockwise. Okay, so if you look at a picture from the opposite direction. You just see it inverted. Okay? Where it becomes more difficult, at least for me, is if your lowest priority is not wedged or dashed. Okay? If it's a solid line. In those cases, I always redraw it. You'll see me draw these things again and again and again. It's because I cannot physically see it in my head. I must draw them out. If you would like to, I'm pretty sure the Khan Academy has other examples or shortcuts as far as assigning R and S. I won't show you any shortcuts beyond what we've already just discussed here because I can never consistently get those shortcuts to work. Okay? And if I can't consistently do it, I'm not going to try and do it for you because if I'm not going to do it right, you probably won't do it right either. Okay? So as frustrating as it may be, I highly recommend drawing a lot to get these things nailed down as far as assigning your R and S. Okay? And at the end of this, if you still like nomenclature, then you're a better person than I. And I guess that isn't all that difficult to do. Okay? So that's our RS assigning. Oh, geez. Okay, let's come back here. What the heck? Give me a sec. Okay, sorry about that. Just lost my connection. Last thing we can go through and do, or kind of summarize everything, assign your priorities. Once you've identified you have that chiral center, reorient the structure so that number 4 is dashed or aimed away from you. Be careful with that too, because 4 may not always be a hydrogen atom. In a lot of cases it is, but that's not always the case. Once the structure is drawn such that 4 is aimed away from you, you can draw an arrow connecting from group 1 to 2 to 3. Look at the motion of that arrow and decide, are you moving clockwise or counterclockwise? If it's clockwise, it's R. If it's counterclockwise, it's S. And in an exam, what I would recommend you do, because it's pretty much a 50-50, when you first get to the question, guess. Write R, write S, pick a guess, and then continue on through the rest of the exam. Come back if you have time and actually assign it and see what your answer is. Worst case, you don't get time to go back and check and you've got an answer written down. 50-50, you might get the points. Okay. Best case, you get time to go back and you check your work. You verify that you did it right. Fantastic. Everybody's happy. Okay. So it works in to your benefit to kind of just at least take a guess on it to try and get it nailed down. Okay. Treatment of multiple bonds. It doesn't happen very often, but you can see double bonds show up as one of the pieces, one of your priorities, either the 1, 2, 3, or 4 positions. In general, the less hybridization, the higher the priority becomes. Okay, that's kind of my hand-wavy assessment. When it comes to the official rule, what you need to go through and do is treat the multiple bonds as phantom bonds. So if we take a look at, say, this is where our chiral center is. Our R group is our chiral center. So let's go ahead and star that. That's our chiral carbon. If we went out, we'd say, oh, there's a carbon there, and that carbon is bound to, let's say we had another carbon out here. So we wanted to identify which of these had the highest priority. Let's make this a little bit more difficult, actually. Let's go ahead and put it in black. If we had our chiral carbon here, and then we had a CH2, CH3, okay, and I want to know which carbon has the higher priority. Which of those carbons is higher priority? So what we'd go through and do is compare the atoms themselves. Same atomic number. Okay, great, no difference, so we move out. We can go out to a hydrogen versus a hydrogen. No difference, so we go back, and we could then say we've got carbon versus carbon. No difference. What do we do now? Now we run into kind of this gray area. Okay. When we're assigning R and S stereochemistry, Okay, remember, it really only applies to sp3 carbons, even when it comes back to our priority rules. Okay, so if you come out to a carbon or an oxygen or a nitrogen that has a double bond, okay, we have to treat that slightly differently. We have to convert that into an sp3 format, if you will. Okay, quote unquote. So what we're going to do is treat that double bond as two bonds to a carbon. Okay, so what this figure is trying to show is that this bond here is the double bond to that carbon. Okay, I know it's really, really weird, but that's ultimately what we're trying to say. Okay, if we still don't find a difference, then we'd have to shift out to the next carbon out. Well, that carbon was also sp2 hybridized with that double bond, so we have to show that it still has that double bond back to that carbon. Okay, so what we end up creating or adding into our structure are what I've been calling, or have previously called, phantom atoms, or phantom, let's just call them phantom atoms. Okay, to represent the multiple bonding. Okay, it's a bit tricky of a process to go through and do, so just add it as an extra bond, redraw it and add it. So in this case, if we're going to try and compare back as we were, that carbon is connected out to a phantom carbon, this one's connected to a phantom carbon. So now when we compare out, I'll go through and kind of scale through this. We start with orange. Those carbons see no difference. Our hydrogen, let's draw on that hydrogen out there, sees no difference. Whoa, that was a big eraser. Okay, we would then move out to carbon. Okay, and carbon, no difference. So then we could move to, try and do it in blue here, carbon versus hydrogen. Which one has the higher priority? That carbon wins, which means this carbon gets assigned the higher priority. So we could give this one, just as an extreme, 1 versus 4. Okay, our lower priority in that case. Okay, when we move up to heteroatoms, again, what we end up doing is adding in that phantom carbon. Because I've been showing them in red, let's go ahead and show them in red on the original structure. This carbon is bound to a nitrogen and bound a second time to that nitrogen. If I had to push further out, that nitrogen is bound to the carbon and a second time to that carbon. Hence the configuration what they're showing over here. Okay, same thing happens with triple bonds or even carboxylic acids. Okay, in general, like I said, what you'll end up finding is that the less hybridization, the higher the priority. So if we go all the way back to our initial example, when we went through and did that, we said our orange carbon, oh, there's way too many colors up there. Let me just draw that again real quickly. When we compared through, there was we had a CH2, CH3. When we compared these two carbons, our two groups, orange versus, red's not very contrasting, let's go green. Okay, when we compared those two, orange took higher priority. Okay, why was it higher priority? Well, we officially went through all of those rules explaining it, but you'll notice what's the hybridization of that carbon? It's sp2. Okay, the hybridization of our green carbon was sp3. So what we're looking at is a decrease in the hybridization. Okay, you decrease the hybridization, becomes higher priority or lower number. Okay. I'm noticing that we're about to come up on the end of our official lecture time. I'm going to be a bit obnoxious and push it probably another 10 minutes. Okay. This is the end of our Kahn-Ingold absolute configurations. So now what we're going to move into is our what was it? I can't even remember what they're called now. Relative configurations. And we said that had to be found through experiment, and that's using something known as a polarimeter. And what ends up happening in that case is we've noticed that a chiral molecule interacts with light differently than, or two chiral molecules, or an R and an S stereocenter interact with light differently than each other. Okay, so what we ended up noticing, or how we found this, I don't know why anybody would build this experiment to begin with, but hey, they did. We took a sodium lamp, okay, or a light source, so it's how they interact with light. We need light first off, and they pass it through a filter. Okay, that filter's there just to make sure the light is consistent and even, and when it passes through that filter, the light has all directions associated with it. Okay, so light can move in any given direction. You end up with different vectors associated, and what they're trying to show is that how that light passes through. Okay, so we get all of those directions associated with it. We then pass that light through a filter, okay, much like your sunglasses, or some people's sunglasses, a polarizing filter. That will reduce the amount of light. So what it'll do is filter out any light that is not in this case, this up-down vector. Okay. So once that happens, you'll notice that when we take a look at the light, the only light that passes through is now in that up-down direction. Okay. That light can now pass into our sample. Okay, and when it first passes in, or starts into it, it's going to be in that up-down direction. Okay. If our sample is chiral, it's going to have an impact on how that light moves. Okay, so if our compound has a particular chirality, as soon as the light impacts that molecule, the light shifts, okay, or rotates off of that complete vertical direction, which is what they're attempting to show in each of these cases. And each time the light hits a new molecule, the light gets rotated further. Okay, so what we end up noticing by the time it passes out of the sample is that our light has rotated a substantial direction off the axis, okay, off our starting position, our zero axis. We can then relate that back to the optical activity of our compound. Okay, and that's where polarimetry comes in, or why it's helpful. So with thalidomide, we could put that into our polarimeter and see, oh, I've got only the R, and we can't call it that. I have only the negative direction. So if we look at our optical activity, you see there's negatives and positive numbers. Okay, so I have only the isomer that produces the negative direction, or only the one that produces the positive direction. Okay, it's a little bit more complicated than that, but that's not as big of a deal for us. Okay, so what we end up generating is a new system. So if the light rotates in the positive direction, we call that dextrorotatory, okay, or it rotates it to the right, okay, clockwise direction, assuming you're moving from 12. Okay, if it rotates light to the left, okay, we end up in the counterclockwise direction, and we call that one levorotatory. Okay, so all we're trying to do is come up with a system that represents that. Okay, and those of you in biochemistry may have already seen this system before. You might have noticed positives and minuses in the nomenclature of your different compounds, or the naming of your different compounds. The other thing that you might have also seen would be the use of D, okay, either lowercase d or capital D, or a lowercase l or capital L. Those are ultimately referring to the chirality of that molecule, okay, which way it's rotating light. Okay, so it's an experimental way to try and determine if your compound has chiral centers within it. Okay, unfortunately, it doesn't tell you how many chiral centers. So you could have some that are R and some that are S. Okay, that relationship doesn't show. Okay, and in fact, you'll one of the more important aspects of this is that it's not related to R and S. So I know when we went through and assigned R, we said, oh, that's when we did our little circle to the right. That has nothing to do with the fact that light is rotated to the right. Okay, so they're two entirely separate systems. Okay, so I know that's tricky, but try and treat them differently. So if I ask you to sign R and S, great, that's one question. If I ask you for optical activity, great, that's another question with a different system, a different naming system. So the plus minus, dextrorotatory, levorotatory have nothing to do with R and S. Okay, so don't cross-relate them. Just because they have nothing to do with it doesn't mean I might not ask a question about it. Okay, I could say you have an R compound, okay, or an R stereocenter. Which way does it rotate the light? Okay, and it might even be a multiple choice. Let's say it's multiple choice. So if I ask that question, I say it rotates, okay, you've got an R stereocenter or an R compound. Okay, so let's go through and say we've got a compound that has the R stereocenter. And then I asked, which way does it rotate the light? Does it rotate it dextrorotatory? Does it rotate it in the positive direction? So two answers, A, B. Does it rotate it levorotatory? Does it rotate it in the negative direction? Or impossible to tell? Okay, so you get all sorts of multiple options there, and in fact you get 5 things, like a standard multiple choice. Okay, except most of those answers are garbage. The only one that's important there is not possible to tell. If I tell you have an R compound, you cannot tell me anything about its optical activity. Okay, they're two different nomenclature systems. You can't cross-relate it. Okay. The next issue with this, okay, and actually I'm going to have to go back here real quickly. When we look at that polarimeter, remember I said that the light rotates every time it impacts a new molecule. Okay, we get a slightly different rotation. So if I test a sample, the same compound that you test, and the concentration's different, I'm going to expect to see a different optical activity than you do. Okay, that's a bit tricky to deal with, so what we need to make sure we do is standardize our results, and that's where we get something known as the specific rotation. That rotation is dependent on the temperature of the sample. Dependent on the temperature of the sample, so if you look it up, you'll typically see a T written as a superscript, and the wavelength of light used. Okay, so what you would end up doing is using your polarimeter to obtain the observed rotation of the light. And then you would also have to summarize the concentration of the sample and the path length of the sample. Okay, so how long did the light have to go through our individual compound? Okay, I won't make you do any calculations with this. I just want you to be aware of it. It will show up in lab. You'll have to do the calculations in lab. Okay. One of the more interesting things here is you'll notice that the concentration is not your standard concentration that you would see in other situations, say like molarity in Gen Chem. What we're looking at is the grams of our target compound, whatever we're looking for, divided by the total volume. So I actually have this slightly wrong. This isn't the milliliters of solvent. This is the milliliters in total. Okay, and that's because your compound takes up some volume as well, so we can't say it's just the solvent. Okay, so be aware of that. You've got your positive and negative directions. It's all kind of dependent on these individual features. Okay, I might ask about what things control your specific rotation, but I won't specify or make you do calculations. Okay, so the things that are important are the concentration of your compound, how much solvent you added, so your total volume, and the path length of the sample cell. So how far does the light have to pass through? how is this important for us? Well, the other common questions that you'll see for this are looking at the optical properties of the stereoisomers. So if we go all the way back again to our 1,2 dichloro structure, our 1,2-dichlorocyclopentane, if I draw out a couple of the, or draw out the stereoisomers, we can go through and trying to answer some questions about the optical characteristics or the optical activity of these. Okay, and some of this is interesting, some of it is, I don't know, kind of boring, I guess. If we take a look, that was sloppy, but it's close enough. When we're looking at enantiomers, okay, enantiomers happen to rotate the light the same amount, okay, the same magnitude for a given concentration, given path length. Okay, but they're going to rotate it in opposite directions. Okay, so let's real quickly assign stereochemistry. So this is 1, we got 4 for our hydrogen, 2, 3, 1, 2, 3. We're moving in the clockwise direction, so this one ends up being RR. The other one here, if we go through and again, 4 is aimed away from us, 2, 3. This one is SS, and the last one will end up being RS. Okay. When we compare our first two structures, what's the relationship between those? Okay. Well, enantiomers, the relationship is mirror images, so or right hand, left hand, or R and S. So if we start RR and we move to SS, our relationship is enantiomers. Okay. If we take a look at our last one, if we have an equal mix of R and S, what we're looking at is a meso compound. Okay, so you could go back to the review slides or review the section where we talked about these. Okay, and if we looked at the relationship between either of our enantiomers and our meso compound, we'd be looking at diastereomers. Okay, so if an individual R chiral center, okay, in this case with our chlorines, if we say this rotates light, let's say in the negative direction by -5 degrees, well, what happens when it encounters this one? Same thing, rotates it by another -5. Our optical activity for a single molecule we might expect to be -10. If we go through and look at the enantiomer for it, okay, it's got the same characteristics, the same groups attached to it, it's just now inverted. So what ends up happening, we can't invert the 5, what we'll end up inverting is the positive, or then plus minus. So instead, this chiral center will rotate light by +5 degrees. So if we look at the optical activity of that molecule, we can predict it to be +10. So the relationship between our enantiomer pairs is that they will rotate light the same amount for the given concentration, but in opposite directions. One will be negative, one will be positive. Okay, so that can be a nice thing to compare, and if you move into more advanced organic, you can actually do all sorts of fun calculations with that, and fun is used sarcastically there. If we compare, look at a meso compound, okay, for our R stereocenter, we said it rotated light which direction? Yep, -5. For our S, it rotated it +5. What's the optical activity for our meso compound? Ends up coming out at 0. Okay, which kind of makes sense. Optical rotation only works for a chiral molecule. Meso compounds are achiral, which means no optical activity. We don't see the rotation in light. Okay, so while optical activity can help us identify if we have chiral centers, it's not a be-all, end-all. Okay, it can help, but it's not perfect. What if I had a 50-50 mixture of the RR compound and the SS compound? Okay, so let's take two molecules now. One's RR, one's SS. When light runs into the RR molecule, what happens? rotates it, total of negative 10 degrees. That light then passes through the sample and hits the SS molecule. What happens? Rotates the light positive 10 degrees. Okay? The net result, we get no optical activity. We don't see anything. That ends up being a special thing that I should have added up here as a mixture or a special statement. If we end up with a racemic mixture, it's a 50-50 mixture, okay, of, let's call them paired enantiomers. Okay, so it's ultimately the same thing as a meso compound. Okay, so if we have a racemic mixture, we see no optical activity. The only time we'll really see optical activity is if we don't have, if we have at least one chiral center and we don't have a meso compound. Okay, could we determine the optical activity when we're comparing diastereomers? Okay, we've changed the order for each of those individual things. If we didn't know that compound on the far right was a meso compound, we wouldn't be able to necessarily predict its optical activity in comparison to our middle or either of the enantiomers, because we've changed the atom orientations. Okay, so our diastereomers will have optical activity, but we can't. Given the optical activity of one diastereomer, that doesn't tell us anything about the optical activity of the other diastereomer. Okay, so we don't really have a nice even comparison. So really our optical activity comes down to comparing three big terms: racemic, enantiomers, and meso. The big thing to remember is that racemic and meso end up appearing as a chiral. They have no optical activity. Enantiomers will rotate light with the same magnitude, but our biggest difference is in opposite directions. Okay, so that's our big key thing from our optical activity. Okay, I know that was a lot of stuff to go through, and I ended up pushing your lecture too long. Okay, so you ended up having to sit through another 15 minutes. I apologize. As far as problems that you can expect on Wednesday, this is what you can kind of see. Okay, so I will try and write up a nice, I don't want to really call it a quiz, but we'll do it in class. It's going to involve me running a couple examples on the board and having you guys work on it on your own as well. Okay, trying to get familiar with what's happening with each of those individual pieces. Okay. Thank you for your patience and your time for listening to an hour and a half of me discussing. Hopefully you broke it up. And I will see you next week.